Okay, so we can start. Let me welcome everybody who joined our seminar today, the second talk in the Optimal seminar for this fall. I have the pleasure to have Professor Mariam Kamkarpour from EPFL. Mariam got her PhD from University of California at Berkeley. Then she was faculty with ETH Zurich and University of British Columbia. And she recently moved back to Switzerland and EPFL, as I mentioned, in the Faculty of Mechanical Engineering. So Mariam today is going to talk about, the title of her presentation is Learning in Multi-Agent Systems with Applications to Electricity Markets. And yes, Mariam, the floor is yours. Thank you again for accepting our invitation.
Okay, great. Thanks a lot, Stefanos, for the introduction. It's a pleasure to be with you here remotely and to share a little bit about my work. So please feel free to ask questions anytime. And if something is unclear or if the sound is not good, just let me know. Okay. So I'm going to talk about learning in multi-agent systems and highlight a few applications in electricity markets that actually motivated my theoretical work. Okay, so multi-agent systems, so they're interacting agents with coupled objectives and constraints. So for example, smart grid, where we have a number of prosumers and consumers that are determining the amount of production and consumption, and they want to optimize their cost, but the cost depends on the decision variable of everybody. Similarly, in an auction, such as electricity market auction, different participants place bids, but whether they get a reward or not depends on the choices of other participants. And similar problems exist in multi-agent robotic systems or in transportation network. Here, for example, the travel time of a car depends on the choices of other cars. So we have coupled objectives. And so the question that we are interested in is, how do agents learn to optimize their cost function, given that they don't know the action of other players, and given that they might not even know the functional form of the cost, because that depends in a non-trivial way on the action of other players. So it's a learning problem. So the outline of my talk, I'm gonna highlight or work on black box learning in games. So this is where we don't have any information about the game except our experience, costs, or payoffs. Then I'm going to make a connection on learning in games and regret minimization. And then I'm going to talk about how to incorporate partial feedback into these black box models to improve the rates of learning and conclusions. Okay, so let's formulate the multi-agent learning problem. We have n agents or players, and they each have an action from an action set. The joint action here is shown by boldface A. And then they each have a cost that the agent's I cost doesn't just depend on her own action, but on action of everybody else except her as well. Okay. So that's why this is a game, not a single optimization problem, because my cost function is not just a function of my decision variable. An example is electricity market prices. They depend on total demands or production, which is a decision of every player. Now, in this multi-agent setting, the notion of optimal local decision is a Nash equilibrium. So an action profile for all agents is a Nash equilibrium if no player has incentive to unilaterally deviate from her choice. So every player is choosing the optimal action given actions of other players fixed. Okay, in a zero-sum game, this has a interpretation as the saddle point here, where the one player is a minimizer, the other one is a maximizer, and here we are at an equilibrium. Okay. So let's talk about how do we characterize Nash equilibria in convex games. So for the first part of the talk, we assume that our game is convex, which means that the decision space of each player is convex and compact, and the cost function is continuously differentiable in its argument, and its convex cost function of player I is convex in her decision variable. Okay, and in this case, it's known that the Nash equilibrium can be characterized by a solution of a so-called variational inequality. How do we form that variational inequality? First, we define what's called a pseudo gradient for the game, which is the stacked version of the gradients of each player's cost with respect to her own decision variable. So we stack this together, and we know that A star is a Nash equilibrium if and only if, in a convex game, if and only if M evaluated at A star, so the pseudo gradient transpose A minus A star is greater than or equal to 0 for all feasible decisions. And this is called a variational inequality problem given the gradient map M, a map pseudo gradient map M and a space A. Okay, so maybe you now wonder, okay, does this look a little bit familiar? If you think of convex optimization problem, this looks like first order optimality condition, right? Of a constrained convex optimization problem. In particular, if M was gradient of a single convex cost function, this would be exactly a first order optimality condition, okay? And this is a big connection between convex games and optimization problem. The only difference is that in a game, the pseudo gradient is not necessarily gradient of a single function. It's obtained by stacking together gradients of each players. And in general, there exists no single function whose gradient will equal M. Nevertheless, the variational inequality framework is general enough that characterizes both solution of a convex optimization problem and a game. Good. So we start with also convex games because we know Nash equilibria exist and we know how to characterize them. Now, let's talk about the problem of learning in games. So here we're considering the case in a black box setting where players observe only their cost functions for a chosen action. For example, if it's real-time pricing, the consumers can see their bill, electricity bill, but they don't know how that price function depends on everybody's action. Or if it's electricity market auction, the participants just receive whether their bid is accepted or not and what's the payment rule, but they don't know the optimization problem that the central planner is solving or the bids of the other players. So they have very limited local information. So if we were to formalize this for player I, she plays an action AI and she doesn't know what's in this box, but she receives a cost JI of AI and A of negative I, which is action of other players. So the first thing we might think is, okay, this looks like black box optimization. So let's use black box optimization methods. For example, let's estimate the gradients of this cost function. And what I want to highlight is there is, again, another difference between games and optimization. And that's the fact that, let's say we use finite difference. So player I queries its cost at AIT and AIT plus some perturbation. As a feedback, she gets JI of AIT and action of other players, but the action of other players meanwhile might have changed. Okay, so if her cost goes down, it's not clear it's because of her action. So if it was a negative gradient approximately, or if it's because of other players' actions. Okay, and so another way to think about this is that in a game we have a 1-point banded feedback because we don't know the cost function and we don't know actions of others. So from perspective of player I, she's just observing a time varying cost function where the time variation is coming from actions of other players. Okay. So we cannot use finite difference because we cannot control this function we cannot control all its arguments. We can only control our own action. But we have to do an approach that only uses 1-point feedback. So let me just illustrate the approach that we propose. So the idea is that we use a randomization to get a 1-point estimate of the gradients of the cost function. So in a high level idea, player I will sample from some probability distribution centered on a mean and on some with some variance. And then she plays AIT equal to the mean plus this noise. As a feedback, she receives JI of t, which is her cost function evaluated at AIT. And then this is the part that she doesn't have control over. And then she updates the mean. So mu I at t plus 1 equals mu IT minus some learning rate eta t times the cost she receives times this randomization. Okay, so this looks like kind of like a gradient descent, except that this is a payoff function. It's not a gradient function. But let's talk about how we can get a gradient estimate using this approach. Well, it turns out that if you think of a smooth cost, which means if you integrate the cost function with respect to this joint probability distribution, the JIT scaled by the random noise estimates the gradient of the smooth cost with respect to mu I. Okay. So by introducing a randomization, we get a 1-point estimate of a gradient of a smooth version of the cost function. Okay. And actually we can bound the bias and variance of this estimate with respect to the gradient of the cost function. So now we have something that looks like a stochastic gradient descent because we are estimating the gradient using 1-point feedback, and we can bound its bias and variance of this estimation. So let's just kind of talk about what result we can show with this simple algorithm. So if we assume that the game pseudo gradient M is strictly monotone, and that's the definition, and also it's Lipschitz, then we can show that we can choose this step size, or in other words, learning rate, and the variances such that this state of the game mu t converges almost surely to a Nash equilibrium. And I want to briefly talk about these conditions. These are very similar to stochastic optimization conditions. And when we just look at briefly at the proof, you will see where they come from. Okay, so the proof idea is based on a stochastic dynamical system theory. We just look at the distance between mu t, so the state of the algorithm, and the Nash equilibrium. And this is our algorithm. We can, as I mentioned, we can write it if we stack every player's state, we can write as mu t plus 1 is mu t minus some learning rate times the pseudo gradient plus a bias and this noise term. The noise term has expectation 0, and the bias we can bound. So once we look at the expectation of the mu t plus 1 minus mu star, so the Lyapunov function at the next iterate, we can bound that by the value of Lyapunov function at the current iterate, plus this additional term, whose order is eta t sigma t plus eta t squared over sigma t squared. And so if we want this to be bounded, this is why we need these two conditions on the step size and the variances. And then we have some extra term here, which from strict monotonicity and the fact that the game Nash equilibrium is characterized by a variational inequality, we can show it's non-negative. And by having the eta t to sum to infinity, we can show that this term then must be converging to 0. So we should converge to Nash equilibrium. Okay, I just wanted to sort of highlight where these step size conditions come from, but the basic idea is that we can perform by using a 1-point estimation of the gradients. We can have a learning algorithm that only uses black box and information converges to a Nash equilibrium. Let's look at a simple example. like a corner game in electricity market. So we have a number of profit maximizing producers. They want to decide their production profile over D periods. So their decision is AI, A1I up to AID for player I. So these are the D periods. We assume they have some local production constraints, and we also assume there are some coupling constraints on network capacity for each period. And the player I's cost function is a combination of some local cost plus the price of the electricity times its production. So this picture, you have to think of it as a production price versus production. So a curve that goes reverse to this. Okay, but they don't know these price functions, and they only get black box information about it, and they don't know actions of others. And the question is, by just observing the price, can they converge to a Nash equilibrium? And so we can just run this algorithm. And in this case, I'm showing the simulation for 10 players who are choosing consumption profile over 2 periods. And I'm just showing the iterates corresponding to 3 random players. And we're looking at the Nash equilibrium is the line in yellow. So they're basically quickly, after some oscillation, quickly converging to the Nash equilibrium solution. Okay, this is for the first coordinate of their decision, and this is the second coordinate. Good. So are there any questions so far?
Yes, just a quick question.
Yes.
I've noticed that your payoff function must be twice differentiable, but I'm just curious, what would happen with the convergence of the algorithm if you have like a linear function? So just
linear would be fine also. The payoff function should be convex in player's I's decision variable. And then you should be able to, like, it should be differentiable with respect to the all variables. So linear would be fine.
All right.
Yeah.
Thank you.
Good. Other questions? Okay. If not, then I move on to making connection about learning in game as regret minimization problem. Okay. So let's talk about bandit learning and neural regret algorithms. So what's that? And this might be a review for you guys, but I just want to make a point about connections to learning in games and what we know so far about this connection. So in a bandit learning problem, so we have a player I is choosing action AIT, and she's faced with some black box that she doesn't know what function here is, but she receives JI of t, so the cost for the played action, okay, at time t. And then she has to design some algorithm that ensures the so-called regret. Her regret is minimized. So what is regret at time t is a difference between the experienced cost functions. So this is JIT evaluated at the chosen actions minus the sum of the cost functions evaluated at the best action in hindsight. So meaning if you know all these cost functions in advance, what would be the single action you would choose to minimize this sum? Okay, so we call an algorithm no regrets if this regret term doesn't grow too fast, basically if it grows sublinearly with respect to time t, okay? And we know no regret algorithms exist for convex optimization problems. Again, look here, we don't yet have a game, we are just looking at an optimization. The player is facing some time varying cost function. What's the connection with game? Well, in a game setting, because we cannot control other players' action, as I mentioned, from the perspective of player I, it is like facing a time varying sequence of functions. Okay, so then we can think that, well, maybe players don't care about Nash equilibrium. They're just observing this sequence of time varying functions such as prices, and they want to minimize their own regret, right? It might be a more reasonable way of thinking how players should act in a setting, in such a multi-agent setting. Well, it turns out that there's a great connection between no regret learning and equilibria. In particular, this connection is very well understood in finite action games. So if each player adopts a no regret algorithm, we know that the average of the sequence of actions converges to what's called a coarse correlated equilibrium. It's a loose notion of equilibrium, which means that it strictly includes Nash equilibrium. But there is some, basically the point is there is some convergence to equilibria. And for certain classes of games, such as potential games, we can show that actually the player, the averaged actions will converge to Nash equilibrium, okay? Or for zero-sum games, but in general, it's a loser notional equilibrium. And so what we showed in our particular algorithm, which was quite simple. So actions were from some mean state plus some randomization, and this was the update of the algorithm. And we showed that we can show that this algorithm is also a no regret algorithm. And in particular, the last iterate action is converging to a Nash equilibrium. So we have a much stronger result. But it's not surprising because we are assuming convexity of the game. So we are making more assumption. Finite action games, in general, not convex. And we also assume the strict monotonicity of the pseudo gradient map and Lipschitz continuity, but I want to highlight the strict monotonicity a little bit more now. Okay, so there is a connection between no regret learning and convergence to Nash equilibrium. And in particular, we can show our black box algorithm is a no regret algorithm. And under certain conditions, it converges, the iterates converge to Nash equilibrium. Let's look at this condition a little bit more and see how restrictive it is. And to highlight that, I'm going to look at a very simple game, which is called Matching Pennies. It's a two-player game. So the two players together reveal a penny, and if reveal each, they have a penny in their hand and they reveal it, and if we have head-head, then player one gets a cost of 1, is zero-sum, so player 2 gets a cost of -1, and if player 1 has a head and player 2 has a tail, it's vice versa. Okay, so it's a zero-sum two-player with two-action game. If you relax, in this game doesn't have a Nash equilibrium, but if you look at the relax the strategy spaces, meaning that instead of looking at 0, 1, you look at the whole interval 0 to 1, and you assign probability distributions, probability of turning head or tail, then it has a Nash equilibrium, and it's a convex game in particular, but its pseudo gradient is not strictly monotone. In particular, it's identically 0. Okay, and it turns out that the learning algorithm that I presented, as well as a large class of no regret algorithms, diverge. So here you see the iterates of the learning algorithm we have for matching penny. It's such a simple game, right? Two players, zero-sum, convex game in mixed strategies. The equilibrium solution is choosing probability 1/2, 1/2 to reveal head or tail. And actually it was proven that all follow the regularized leader, which is a large class of no-regret algorithm, diverge for this problem. Okay. And so this is just one example where strict monotonicity is not satisfied. In general, if you have a zero-sum game that is convex concave, you may not have a strict monotonicity. And because of this, this problem has been studied a lot. One interpretation is that you can think of this game from a Hamiltonian system perspective. So if you look at the gradient, of this pseudo-gradient map, there is a symmetric part and there is an asymmetric part. If the game only had this symmetric part, then it would be a potential game, and finding the Nash equilibrium would be exactly equivalent to an optimization problem, because there will be a single function that players are all trying to optimize. And if the game has only the asymmetric part, which is the case for matching pennies, this is like a Hamiltonian system where the energy is conserved and basically you rotate around these optimal decisions. You never converge to an equilibrium using these general class of no-regret algorithms. Okay, so, and in general, the game might be a combination of these two, but for convergence to Nash using these no-regret algorithms, we need the strict monotonicity. So what can we do in the case of non-strictly monotone? I just very briefly present our solution. So here we relax the assumption. We don't have a strictly greater than 0, but we allow this to be also equal to 0. And we introduce a regularization to the algorithm, similar in spirit to the so-called Tikhonov regularization. And by introducing this regularization, basically we're making the game strictly monotone, but this epsilon t has to converge to 0. And the challenge in analyzing this algorithm is how to properly choose the rate of decrease to 0 of epsilon t, eta t, and sigma t to ensure convergence to the Nash equilibrium. And I won't go through it for the sake of time, but I just want to highlight that this is doable basically. And it's again a black box learning algorithm, because we don't need any other information. We don't need, it's not an extra gradient method. Which is another way to deal with this, because we don't have gradients basically. So we only use each player only uses her action, which she already has access to update the iterates. Okay, and then you can see convergence in matching pennies and other non-strictly monotone convex games. Okay, I'll just pause to see if there are questions so far.
Mariam, I don't see any questions also in the chat, so I
think. Okay, perfect. Continue. Okay, so now we talked about black box learning in games. So learning Nash equilibria with only the experience cost information, the connected learning in games to regret minimization problems. And now what I want to talk about is how do we incorporate partial feedback? So a lot of practical examples are not completely black box. Okay, for example, in a transportation network, we see our experience travel time, of course, that's one of the feedbacks, but we can also observe congestion on the roads. Okay, so we have more information. In an auction, we don't only see whether we won or lost on our payment, but we also sometimes we see usually the prices, electricity prices, and we also sometimes see the winning bids. Okay, and I want to talk about how can we incorporate this additional information in learning. And I'll talk about we thought about this problem using 2 different approaches, and I'm going to talk about these approaches now. Okay, so just as a warm-up, we are also going to look at more general class of games, because these auction problems or this transportation planning problem are in general non-convex. Okay, so the convexity assumption may not hold. So we're going to look at general non-convex problems. So let me go into then no regret algorithms in non-convex game. In general, characterizing or learning equilibria is sort of hopeless in a much harder problem in non-convex setting. but we can still have no regret algorithm, and that could be a desired property from the player's perspective. So let's say that we have a cost function for player I, ji. It depends on, again, on every player's actions. And we just for now consider that we have finitely many actions, 1 to n, and this can be coming from discretization of a continuous action space. And as I mentioned, no regret algorithms for finite action games are quite well studied. And one of the most famous algorithms is the so-called multiplicative weight algorithm. So let me talk about this algorithm. It starts with a set of weights. Player I is putting uniform weight on each of her actions. Eta is her learning rate. Then for each iteration of the game, she draws an action from this distribution on a probability distribution in the set of actions. Then she obtains a cost, okay? And there are two cases which I will talk about that. So she obtains a cost at time t for every k in her action set. And then she updates the weights proportionally to the past weights multiplied by e to the power of minus eta experience cost for every action, okay? So this is a vector and this is a vector, and you're multiplying the weight of each action by e to minus eta, the cost of that action. Okay, so let me talk about this line about obtaining cost. So there are two cases that are well studied in literature. One is the full feedback, which means that you observe your cost for every action chosen. Okay, so you get as a feedback ji of k if you're playing in a game for every k, and at minus I is the action of other players. The other one is called banded feedback, which means that you only receive the cost for your played action. And in this case, you can form an estimate of the cost of each action by choosing this j hat I of tk to be your experience cost divided by the weight of that action. If k equals the played action, and otherwise you choose it to be 0. And this estimate can be shown to be an unbiased estimate of your cost for every action. Okay, are there any questions about this algorithm? I think you might have seen it before. So it's a sort of a standard no regret algorithm in a finite action setting. And so what do we know about this? In case of full feedback, it's also referred to as the hedge algorithm, and its expected regret of player I would scale with the square root of the time horizon log of the actions. If it's banded feedback, which means that you don't actually receive feedback for every action, then expected regret has also a square root dependence on number of actions. So these are the two extreme cases. Yeah, question? Oh, there's a chat question.
Yes, there is a question from Jalal.
Can we try every single action in every time? You can, so the way you choose the action is, so you update the probability distributions on the actions, and then you basically draw actions from this distribution. So whichever turns out, you try it. Does that make sense? If you query your cost, or you play that action. So if you have like you toss a coin with this, that sort of bias with these weights, and based on the action that turns out, you play that, and as a cost, then you receive in the banded feedback just the cost of the played action. The full feedback, you actually receive the cost of every action. Does that help answer your question?
Mariam, May I also enter here just to ask, how does this bias come from? Like, why this distribution can be biased? Why weights are not uniform, but can be concentrated over some actions, but not
We
over
start
other?
uniform, they start uniform,
Mhm.
right? But the idea is that we should update this weights based on how much the cost of these actions were. So if the cost of some action was high, we should decrease its weights. And that's what this algorithm is doing, is updating the weights based on, in advance, we don't know how we should choose them. So we just simply choose them uniformly because we don't know the functions in advance. And then as we play, we get feedback about cost of different actions and we update the weights. That's how they become biased.
Mhm.
And this way of updating, it's known that it achieves the lowest regret rate, which in the full feedback case is this type of scaling. So it goes to with the square root of t log n, the number of actions. And in the banded feedback, again, this is the optimal rate, square root of t n times log n. And this is the price, the n, that number of actions, is because we only see the cost for one action, not for every n action. And we estimate the cost for the other actions. And then, as I said, we want to see what can we do in between these two cases. We are the banded case. We talked about it. We also know we converge to coarse correlated equilibrium in general. And then in the full feedback case, it's a little bit perhaps unrealistic that we receive the cost for every action, because we only, in general, if we are in the driving or in the auction one, we usually receive the cost just for the action we played. Okay.
Can I ask a question?
Yeah.
So, Mariam, sorry.
Yes.
So here we don't need any more to observe how our rivals respond or not. So,
How what? Sorry, how?
How the others, they respond to every single action of us. So we don't need to see the rivals' actions.
Actually, I'm gonna exactly talk about that. You see, can we improve the rate if player I can observe others' actions, basically? Perfect. So that's exactly what I will talk about now. And the motivation, for example, if you look at a transportation network problem, is, well, you actually don't need to see everybody else's action, but it's sufficient to see the aggregate of their action to know the congestion of the road, right? So how can we incorporate that information? So our cost function might depend on others' actions in a total summation way, and if we can observe that summation, then can we improve the regret rate? And the approach that we used for addressing this problem was to, we have to somehow learn the functions that we are trying to optimize. So we went to a Bayesian approach. Okay, we just said that let's say that our agent I's cost function is a Gaussian process. And actually the motivation was also because I was working with a computer scientist on this problem, which Gaussian process is quite popular there in terms of modeling functions with some prior and then obtaining information. Okay, it's just a way of trying to learn the functions that are completely unknown. So what's the Gaussian process? It's the distribution of the functions. This has a mean function and it has a covariance function. And there are different ways to choose this covariance, which is also called a kernel. For example, polynomial or square exponential. And a priori, you can draw samples of these functions. So these could be all samples of a Gaussian process with a fixed kernel. Okay, and then we are saying that we are making observations about this action, about the experience payoff. So we want to learn this function over time. Okay, so we observe, player I observes her cost function evaluated that at AL, at time L from 1 to T, and this AL includes her action and She also observes actions of other players. It has a noisy observation. We allow the observation to be noisy with some variance sigma. And then it formulates a regression problem. So it just puts these observed costs in a vector and forms this covariance vector and a covariance matrix. And this is how the posterior distribution of Ji given this observation looks like. So the mean is updated based on this information, the experienced costs, the covariance function evaluated at the actions chosen. This is the variance of the noise. And this is the variance between the selected point and any given arbitrary point. And the variance, the uncertainty about the function is also reduced as such. So KAA minus this reduction in the covariance based on the observations we made. So this is just if you have a jointly Gaussian random variables and you observe some of them, this is sort of the way to update the information about mean and variance of the other ones, because by observing this, you have reduced uncertainty about the other variables. So for example, if these were samples of our functions, and this gray area is the uncertainty we have about the function. And if we make observations at certain points, then uncertainty at these points decrease, but uncertainty away from these points is still large. Still, we have a distribution on the functions, and there is a mean function, and then there is a covariance or a variance at every point of this function. Okay. So now we say that let's incorporate the fact that we're learning the functions in our no regret learning algorithm. Oh, so let me just introduce one more concept, which is concept of lower confidence bound on this Gaussian process. So this lower confidence bound is a function. LTA is defined as the mean function, minus beta times the variance of the function. And it's past work has shown that if you choose beta appropriately, then with high probability, this LTA will be a lower bound on the true function. And this beta choice depends on what's called the maximum information gain, which means that how much you could learn about these functions by if you were choosing these points that you're making observations optimally. Okay, the point is that with high confidence, we can have a lower bound on the true function. And we use this lower bound in the multiplicative weight update algorithm. Okay, so how does our algorithm now look like? Again, we initialize weights uniformly at the beginning because we don't know in advance which action gives us better rewards. Eta is our learning rate. We sample the actions according to this weight at each time. We observe now, well, we know our own action, we get a payoff of our experience cost, and we also assume we observe other players' actions, so we know the argument to this function. So we can use a GP regression to learn this lower confidence bound function. And then instead of using the J-hat estimate that I talked about before, we use this lower bound and to update the same exact update rule, except that instead of their cost functions, which a priori we didn't know, now we use our estimated lower bound function as a cost function for every action. Let me see if there are any questions. Okay, no, then we can show that this algorithm is no regret, and by properly choosing the learning rate, then with high probability, this is the form of the regret. I'll just regret we already defined, so let me just compare it with Hedge, which is the full feedback model. This was a regret. This XP3 was a banded feedback, which means black box, and we don't see others' actions. We only see the cost at the chosen action. And then this is the algorithm we introduce, which is, so you see that the dependence, linear, the square root dependence on n has disappeared, and we are happy because this number of actions can be large if, for example, we are discretizing from a continuous domain, okay? But we all have this extra term that arises from the information gain, how much we can learn about these functions, okay? And the point of this is that, so these games are a special class of banded learning problems, and perhaps by exploiting their structure, we can improve the regret bound. Okay, there was an application to transportation, but I don't want, there's a proof sketch, but because of time, I don't go through it. And there was an application in transportation network, which I also don't go through because I think application electricity market is more interesting here. So I want to come to electricity markets. And actually, this is again a different setup of partial information. And it turned out that we had to do something else to our multiplicative weight update to make it suitable for this electricity market auctions. So I'm going to very briefly, I know time is short, go through the setup and talk about the algorithm and show you some simulation results for electricity markets. So here, player i's action could be a set of bits or bit curves, power and price. And the feedback can be the bits accepted and the payment, such as LMP, the market price in the LMP markets, or in some cases, such as the Swiss reserve market, you might see winning bids of other agents. And I want to talk about how we can incorporate this information to improve the regret bound. It doesn't quite fit into our GP model. And that's why we are working on making that GP model fit for electricity markets, but we don't have yet results on that. So, but we tried another way to update our multiplicative weight algorithm to account for this particular feedback that arises in electricity market. So I'll briefly talk about that. We define what's called a probability of learning about bit k's outcome by playing AIT, okay? And so we define then the estimate of the cost function to be ji of tk divided by probability, this revelation probability. If this revelation is greater than 0, otherwise 0 for the cost of that action k is 0. I will talk about how we learn this probability in a second, but let's for now say that by observing bit k, we might be able to infer something about other bits. Because, for example, if we have a losing bit, then we know that if we bid higher, then that would also be a losing bit as well, okay? And so then we can show that if we define a quantity called average information gain, which depends on these probabilities and the weight of the chosen actions, and choose the learning rates appropriately, then our regret scales better in terms of number of actions. So n divided by alpha I average, and this is the same as before. Good. So let me talk about where we can apply this. So here is, for example, convex electricity market clearing under marginal price. And it turns out that in these electricity markets under a strong convexity and the bids being 0 at 0, and well, maybe this I said single linear constraint, but you can generalize it to other constraints as well. In these cases, if you observe the LMP prices, that gives you information, and compare that to the derivative of your cost function evaluated at x equal to 0. If that derivative is greater than the LMP price, it means that your bid will be a lost bid, and otherwise it will be a winning bid. So it means that by knowing the LMP price, you can observe all your basically losing bids, okay? So we kind of looked at this game and looked at the performance of the proposed algorithm. So the idea was what we show is marginal prices reveal information about all losing bids. Here's a simple setup with 3 bidders with strongly convex quadratic costs. They each have n actions that here we just assume they can perturb the linear term of the cost. And then this is the regret. This hedge is if we had full information, full feedback, whereas this extended XP3 is our algorithm, which means that we don't have full feedback, but we observe LMP prices, and this is for different choices of this average information gain. And then XP3 is when we have just black box feedback. So we are doing that each player, the average of the regrets is kind of in between the black box and the full feedback case. We're doing better. Okay, I'm gonna show one more example. This is a Swiss reserve market. So it's a little bit dense, but there is more information in the paper about all of these examples. So the Swiss reserve market is a 2-stage market with secondary and tertiary reserves, and the markets have a weekly and daily couple. It's very complicated constraints from that the social planner is solving. So players can have no way to know how their bids are accepted or not, but they submit a sequence of power and price, and then they can observe whether their bid is won or not, and who are the winning bids. So this is the feedback information they had. And based on that, we can show that by observing a losing bid, any other bid that's in its epigraph, so it's at like a higher cost, will also be a losing bid. And that gives us this revelation, this probability revelation property of learning about other bids, and tells us how to update the alpha in the multiplicative weight algorithm. And so here you see again the result of the regret of average regret of, we have 6 learning agents, and each one has 6 actions corresponding to inflating the bids. This is based on the real data, inflating the bids that they had submitted. And this shows the regret for, again, under full information, which is not realistic. And then this is under black box information. And then this is under the information that observing whether we have lost or not, and trying to infer, and the bid and the other winning bids, and trying to infer other losing bids of ours. Okay. Good. I think with that, I end to leave some time also hopefully for a couple of questions. So I talked about algorithms for learning in multi-agent systems, talked about learning Nash equilibrium using black box information in convex games, and I talked about minimizing regret under partial information in non-convex games. I highlighted application to electricity market. It's actually has been always my motivation, but I always feel I can do more in terms of the application, and that's something I like to further use the algorithms for. Happy to hear your inputs about that. And so now in terms of theory, what we're looking at is learning in dynamic games. So a lot of games, the players change over time, the constraints of the optimization change over time. Here we are assuming the game is staying the same and static. So how do we incorporate this? How do we improve rates of convergence and regret rates using different information oracles that might be realistic in markets or other setups? And also mechanism design integrated with learning. So if we think of what market mechanisms can optimize social efficiency, given we know that players are strategically updating their bid, how do we solve this problem in a coupled way? And with that, I'd like to thank you for your attention. This is the work was with my first PhD student, Orchun Karacha, and another PhD student, Giuseppe Cesar, and my collaborator, Tatiana Tatarenko. This was mainly done during my ERC grant as I was in ETH, so just ended a few months ago. And here are some references, and I'm happy to answer any questions if there are any. Thank you so much for your attention and for the invitation.
Thank you very much, Mariam. It was a great presentation.
Thank you.
We have a few minutes. We want to keep it to 1 hour. If there are any questions from the audience, feel free to raise your hand or just unmute yourself.
I hope it was at a good relevance.
Yeah,
Yeah,
let
yeah.
me ask you a quick question. I mean, more in
Yes.
terms of, because you mentioned also different applications in electricity markets.
Yes.
As you were talking, I was wondering if those learning algorithms could be applied also to continuous markets, like, you know, the intraday market that we have in Europe, that it's not strict auctions in terms of time, like the day ahead or the reserve market that you presented, but it's more on a continuous basis.
Like continuous time, you mean, or how is it?
Yeah,
exactly?
yeah. So it's not the intraday market in Europe. It's, you know, it's there's no single time step where you have an auction, or on a continuous basis. So you match bids and offers from different producers and consumers. So I was thinking whether this could be, those algorithms could be applied in a setup like that, or you need a specific time.
No, they can be applied, because the point is that you place some bids and you get feedback, and that's from that feedback you want to learn how to update your bid, and that's what these algorithms do. What their limitation right now is that we don't assume, we don't model these time variations in the market. So if we consider the fact that the constraints that social planner is solving is also changing with time, then it changes a little bit the cost that you're experiencing, and that needs to be incorporated in the learning algorithm. So they can be applied as it is, but I think it can be improved if we somehow find a smart way to incorporate the fact that the games themselves are changing with time. It's not an identically repeated game, it's a slight modification of that, and that's an interesting problem I like to address.
I see. Yeah. Thanks.
Thank you.
Any other questions? I mean, it's already we're already close to an hour, so if there's any final question.
Yes, I have a quick question about the application with electricity markets. So when you to run your algorithm, you need to randomize a bit, right? You randomize the linear part. I'm just curious, what's the range of randomization? Say that the linear term, I don't know, 50 euros a megawatt hour, right? What's the range of randomization?
I have to see what we chose in that paper.
Just to give a feel, just to give a intuition.
It really depends on the. When you see my screen, if you don't, it really depends on how big the bid is.
I can imagine.
To see, for example, I think. This was the quadratic bid, and then we randomized the L plus delta. Delta in this case was chosen from uniform distribution in interval -6 to 30. So going a little below and above. The costs were of this order. So maybe it gives you, but I think the quadratic terms are also reported somewhere, so this maybe gives you a little bit of idea, but I think if you had written it in percentage wise, probably it would be more helpful. In this is in this case, in the another example, this is the 14 bus delta, so we perturb both the quadratic coefficient and the linear coefficient with this sort of range. And I think that
I think it's a substantial randomization of the bid.
You think it's too large, basically?
No. I don't know what is too large or too small, but just a relative to electricity price.
I think exactly. Yeah. I think probably if I report them in a percentage wise, it's more helpful, actually. Thank you for the question. Yeah, let me just quickly check the chat.
Yeah, there's
Yes, have
one
you
question in the
covered,
chat.
yeah, games with shared constraints? Yes, exactly. Oh, this is a good question. So actually, the paper we have where, let me just share again, that the first part that I presented, there was extension to coupling constraints. That's exactly the one that I said there is network capacity limits on how much each producer can produce. So let me just show it here. This was the coupling constraint, but I didn't go through the theory of it. We actually considered coupling constraints and learning algorithms, and we could also show that here we need to introduce the coupling constraint like a Lagrangian way and add it to the cost function, and then use the learning algorithms, and we can show it converges. But actually, we haven't shown any connection about whether we still have no regret property or not. So the coupling constraint case is less well understood in terms of regret. And we also had to assume a strong monotonicity. We don't have result for just merely monotone with coupling constraint. That's a good question.
But have you obtained like, do you have guarantees of convergence under constraints?
Yes,
or...
we have guarantees of
Oh,
convergence. Here I show you the paper.
Yeah.
Let me just see.
Yeah, which one? I'm not sure if you can put it up. Yeah.
Yeah, I'm gonna. I think now I need to share my screen. Stop share this and start share.
So you said the idea is to add the constraints in Lagrangian form to the course,
yes,
right? Okay.
Yeah. Oh, okay. So this is the paper, and it's called generalized Nash equilibrium.
Yes. Exactly.
Okay, good. You know about them.
But
so
do
here,
you? Yeah. Sorry. Do you think this still works? Because you said generalized
here it
Nash
is
equilibrium.
exactly.
But,
you see,
but
this
okay,
is
yeah,
the
I
one,
see.
the lambda.
Yeah. Okay. But do we also, since regret minimization guarantees convergence towards the set of correlated equilibria, right?
In general, yes.
In general.
But for, yeah, go ahead.
So, like, why are you just looking at Nash equilibrium in this? Did you take a specific class
Because
of
here
games?
we have under convexity, you can show more. You can show convergence to Nash. But if you don't have convexity, the best you can show is this relaxed notion of equilibrium. So here we're still assuming convexity. And the algorithm is exactly the same, except that our cost is updated with that lambda multiplier, you see. And we can prove it converges to Nash equilibrium, but we actually haven't yet shown that this is also a regret minimizing algorithm.
Okay. All right.
Thank you.
Cool.
And the lambda multiplier should be also updated. It's just a standard kind of this primal dual update algorithm, but with payoff information instead of knowing the gradients.
Okay.
Yeah. Thank you for the question. Okay, and any other last minute? In case you have some questions or want to discuss anything, please feel free to email me. I'm happy to discuss. I have to leave now, but I would be very happy to take questions like via email. And I just thank you for your time and for invitation again.
Great, Mariam. Thanks a lot for your time. I think we can conclude the seminar for today. We'll see you in 2 weeks, right, Vlad?
Yes, we'll get back to you all 2 weeks. Thank you, everyone, for joining.
Thank you very much, everyone. Thank you, Mariam. Bye.